Alright, noise floor, headroom, and dynamic range. We're kind of moving back to microphones and sound systems move into this topic, but I bring this topic up at this point after we've talked about frequency and in particular about amplitude, because you really have to understand what amplitude is more than anything to understand how noise floor, headroom, and dynamic range work. And basically what we're talking about is the sensitivity and area of volume that microphones and speaker systems and recording systems work within, and how in terms of how quiet can a system record or how loud of a sound can a system record. All right, first, to understand what headroom, noise floor, and dynamic range are, you really need to understand the basics of how microphones and speakers work. All right, there are lots of different kinds of microphones out there. They all have certain things in common. I'm going to be describing what is called a dynamic microphone. There are condenser microphones, but we're going to be using the dynamic microphone. Condenser microphones, the principles still more or less apply, but dynamic microphones are a little more simplified. All right, as we've discussed, sound information exists as patterns of air pressure, and the microphone changes this information into electric current. And if you look on the picture here, sound will fly into this diaphragm on the microphone. Sound waves cause movement of this thin diagram here. So this diaphragm hits, and there are these wires all wrapped around it. So sound waves cause a movement of a thin metallic diaphragm, and an attached coil of wire wrapped around a magnet produces a magnetic field which surrounds the coil, and the motion of the coil causes current to flow. So essentially what's happening here is this diaphragm here is wrapped around this magnet here, and as it moves forwards and backwards and forwards and backwards, it generates electric current that goes down these wires. And um, essentially the principles for this are very similar to how electricity is produced in a power generator. Here is again is a close-up of a microphone. And then down here is kind of more or less a diagram of how a generator works. In a generator, you have a magnet, you have a piece of metal that spins around within that magnet, and that magnet causes electrons to move within those wires, which causes current. So, I mean, you're essentially what you're doing is you have a very mini power generator that's producing this signal. And you see here the signal. This is reproduction of the signal that's coming out, and this is just current that is going out. Biggest difference between the two is that in a power generator, it's a constant current going out, while with a microphone, it's a varying current. It's changing. The current that is produced by the motion of the diaphragm and the amount of current is determined by the speed of that motion. So depending on how strong or how weak or how high or how low that frequency is, that will change how this diaphragm vibrates. In essence, the generated current mimics the frequency of the audio. So if you look here on a regular power generator, it is a constant frequency. It spins at a constant rate. It spins at a constant rate, creating that electricity. On the microphone, because sound and frequencies are variable, it will be sometimes stronger, sometimes weaker in terms of the amount of force making that coil go backwards and forwards, creating a current that is distinctive to whatever the frequency happens to be. All right. The intensity of the current is extremely low, though, because power generators, they have huge magnets and huge systems that are spinning to create huge amounts of electricity. But for a microphone, not so big. So to be useful for the recording or other electronic processes, the signal must be amplified by a factor of over 1,000. So what happens is that that coil spins back and forth, and then it does create a current at a very specific frequency, and then somewhere along the line in the system, that current is then amplified, made stronger. It's still the same, same frequency in terms of the current goes, fluctuates at the same frequency that it was at, but it's given more power. And then coincidentally, or not coincidentally, but then also just so you understand on the flip side of this on how a speaker works. Speaker works more or less the same way. You have a coil of wires over a magnet. The electricity that goes over that magnet, or the electricity goes through those wires, causes that magnet to vibrate back and forth at the same frequency that it was recorded at the microphone end. And that vibration hits this drum, which then vibrates and hits the air, which recreates that sound. All right. Because of this, any electrical noise, because there's an inherent electricity in the system, electricity is how microphones work. And because there is electricity in the system, there will always be a certain amount of electrical noise produced by the microphone. By the microphone. And since it is amplified, since the sound picked up by this is then before it goes out to hit the speakers, that audio is amplified. Whatever is amplified, and all the microphones have at least some level of noise, that sound can be like a quiet static hum. So just a microphone sitting still with no noise in the room or in the space that you're in, there's always going to be, just by the nature of you got a magnet and you got wires there, you're always going to have a certain minimum amount of electronic noise happening through the microphone. And that noise is going to be amplified, which can cause troubles. The noise floor. When we start talking about our noise floor up here, the noise floor of a system is the level at which you are trying to record something so quiet you need to amplify the signal to the point. When I say amplify in this case, I'm saying turn the volume up. But you need to amplify the signal to the point where the background noise is heard. All right, so when we're talking about amplifying the sound that you're hearing from the microphones, essentially you're talking about turning the volume up. You're turning the levels up, turning the intensity up of what the microphone is capable of recording. Well, there's always going to be some point where you turn the volume up so loud you're gonna hear that little hum sound, or sometimes a hiss sound. That can happen. And you've all done it. If you ever turn the volume up way loud on your TV sets when nothing's actually on, you can kind of hear this little static, little sound in there. That's what you're hearing, is then you've turning it up and you've reached the noise floor when you hear that. And all microphones have that. Better microphones have a lower noise floor than others, but all microphones, all speaker systems have noise floors. On excuse me. On the flip side of that, let's say you're recording something that's extremely loud. You may hit what is called the saturation point. What is a saturation point, you may ask? The saturation point of a system is the level at which the audio becomes noticeably clipped or distorted. This is the point at which the system is overloaded. Essentially, one way to think about it is that this diaphragm here can only vibrate so far, forwards and backwards. If something is so loud, that diaphragm is gonna slam into the back of that magnet, or you know jump back to the back of the magnet. It's just gonna hit a limit in terms of how much movement this diaphragm can actually make. So if something's too loud, the volume's too extreme, that's going to, clipping is a good way of looking at this, because that diaphragm will clip into the back of that magnet and just hit. In fact, some microphones can be destroyed if you record system sounds are too loud, or if you have a microphone where it consistently has somebody shouting into it all the time. Some microphones just can't handle that, and the microphones will become damaged over time. All right, where does headroom and dynamic range come into play? Well, somewhere between the noise floor and the saturation point, there is what is called the nominal level. This is the measurement of a reference point. It is essentially what is called 0 dB. This is kind of considered it's not the middle ground per se, but this is kind of what's considered normal. It was said it's the normal level. It is kind of the baseline sound. It's sort of like where you get the, I wouldn't say it's the optimal recording point for the microphone, but it's where you definitely won't be having any noise in the system and still be starting to get a decent recording. Headroom. All right, the headroom of a system is the level difference between the nominal level and the saturation point. So when you ask about how much headroom does a microphone have, the headroom is based off of that nominal level. Where is that nominal level is? You'll find out where the headroom is. All right. The levels of noise, the levels of the noise floor and headroom are measured relative to the nominal level. So on a typical microphone, your system might have an 18 decibels of headroom. This would be called a plus 18 dB above the nominal level, and a negative 72 dB noise floor, and this would be called a minus 72 dB below the nominal level. All right, so if you're going to be buying a microphone, this is where it sort of falls into the real world type thing. You'll be wanting to take a look at, well, how much headroom does this microphone have, and what's the noise floor of this microphone? And when you buy microphones, or you buy headphones, you buy any kind of a sound system, they'll have these ratings on there if you're looking on the packaging. So this is how you can tell how good a system is. How much headroom do I have on this? Which essentially means how loud a source can I record on this? What's the noise floor on this microphone? Which means what's the range? How low of a sound can I record before I start hearing static off this microphone? What this all boils down to is what is called the dynamic range. The dynamic range of a system is the range between the headroom and the noise floor of that system. It means how many decibels do I have to record between the quietest point on the system I can record before I get noise and the highest sound I can record. What's that range? So looking at the system we looked at before, or the example that I just gave 2 slides ago, if our noise floor is minus 72 dB and our headroom is plus 18 dB, that means we have a dynamic range of 90 dB. Because if you take that minus 72 below the nominal level and add it to the plus 18 above the nominal level, that gives us a 90 decibel range that this microphone or the speaker system or whatever system is capable of working with. And that's about it.